course. All right, so that's great. What do we care about these polyprotic acids, though? So for the most part, what we will be doing with these guys is, of course, determining the pH of these solutions. And what's nice, even though they seem kind of tough, is that for the majority of polyprotic acids, you don't have to worry about the second ionization. Because again, Ka2 is so small, comparatively to Ka1, that when we're trying to calculate the pH, all we have to care about is the first ionization. Okay? There is one example, or one essentially exception to that, and I'm going to cover that in a second. But for the most part, with respect to all of these polyprotic acids, if all I want you to do is calculate the pH, all you have to do is look at the first ionization, and you'll be able to calculate the pH from that. Okay? Another little thing to note, and we'll go over this in a second, but in general, if we have these multiple ionization steps, the concentration at the very end of this equilibrium problem of the fully deprotonated conjugate base is going to be equal to whatever that last ionization constant is, okay? And again, when we run through these examples, I will illustrate what I mean by this, but just as a nice little rule of thumb to put in the back of your brain, the concentration, fully deprotonated conjugate base, is equal to that final equilibrium constant, okay? Okay, so other things. Here's a nice little chart of a couple of these polyprotic acids with their corresponding Kas. So again, if you go through these, you will note that the first Ka is much larger than the second Ka, so on and so forth. But for the majority of these guys, all of their first Kas are weak, right? They're all much less than 1. There's only one exception to that. Which acid has a strong first ionization constant? Sulfuric acid, right? So we've always said, or at least I've said, oh, there are 6 strong acids, right? And sulfuric has always been one of them. But it's important to note that the only strength, or the only strong ionization, is the first ionization for sulfuric acid and not the second ionization. This ends up being a weak ionization in the second step, okay? Okay, so how are we actually going to deal with this? The only thing that you guys have to consider when dealing with these sulfuric acid ionizations, or these polyprotic ionizations, when you have to consider the second ionization, comes in the form of sulfuric acid, because its first step is strong, okay? So I'm going to show you how to calculate the pH of a sulfuric acid solution, because again, this is the only one where you actually have to consider the second ionization. And then I'm going to let you guys try one on your own, okay? All right, so what's going to happen with respect to these types of problems? So let's say that we have a sulfuric acid solution, and it has a concentration of 0.5 molarity, okay? And I want you guys to find the pH of this 0.5 molar sulfuric acid solution. So again, this is the only type of solution where you have to consider both ionization steps, okay? The first one that we consider is the first ionization step. So if I wrote that, if I took my little sulfuric acid solution, H2SO4, and I wrote out this ionization reaction, I would write this with a single-headed arrow, because I know that for Ka1, this is a very strong product-favored equilibrium. My products are H3O+, as well as the conjugate base of H2SO4, which is HSO4 1-. So then again, Ka1 here is strong. So I've got a 0.500 molar solution. What can I assume about my two products when this guy reaches equilibrium, because my Ka1 is strong, or much greater than 1, much greater than 100? So strong acids, what can we assume about how much product we form? Complete ionization, right? So what can I assume about how much of the H3O+ I have and how much of my HSO4 1- I have? It's the exact same concentration, right? I have 0.500 molar and I have 0.500 molar, because again, it's a 1-to-1-to-1 ratio. Okay, so that's the first step, first ionization. Unfortunately, for sulfuric acid, if we want to know the accurate concentration of H3O+ plus, why can't I say that right? I don't know. Okay, if we want to know H plus concentration accurately, we now have to consider the second ionization. Okay, so in the second ionization, we've got our conjugate base, HSO4, reacting with water. This guy comes to equilibrium because we know this is a weak acid. We have a Ka associated with it. It's going to form H3O plus the fully deprotonated conjugate base, which is SO4 2 minus. Okay, so now this guy has a Ka. This is Ka2. It is not strong. It has an actual value 1.2 times 10 to the minus 2. So now we have a weak acid equilibrium, we have a Ka, we have some initial concentrations. How are we going to go about solving this problem? Again, we're trying to find H3O plus at equilibrium. So it's probably going to involve an ice table, right? So we have a little ice table out to the side. I'll go ahead and draw it. We know a couple of things about this guy for these initial concentrations, right? What is my concentration right now after that first ionization of HSO4 1 minus? 0.5, right? So this guy, we already know, is 0.5 molar because of that first ionization. So this is 0.500. Again, we don't care about water. What about my two products? So what do we normally assume about products? 0, right? But there's only one little slight difference here. One of these is 0, right? One of these has not had any chance to be formed yet. So one of these, the fully deprotonated conjugate base, is 0. But what about H3O plus? Do we already have a concentration for it? Yes, it's already at 0.5. So this is the big difference here. This guy is 0.5 initially, right? We haven't really seen something like that before. So now that we have our initial concentrations, how are we going to represent our change here? Probably some unknown variable x. So again, our reactants are going to lose x. Our two products are going to gain x and gain x. And at equilibrium, we will sum the columns and be left with 0.5 minus x, 0.5 plus x, and x. This guy is our second ionization. Okay, so now, again, we're trying to determine the pH of this solution. So we have to solve for H3O plus at equilibrium. Okay, so I'm going to utilize my Ka here. I know that the equilibrium constant for this reaction is 1.2 times 10 to the minus 2. I'm going to go ahead and plug in my values for my equilibrium species in terms of x. So for my products, I have 0.5 plus x and x. And both of these are going to be divided by 0.5 minus x. Okay, so what would be nice and helpful for us to simplify the math of this problem? So what have we been doing with respect to this guy on bottom? What have we been doing this entire time? Been ignoring it, right? We've said, oh, x is going to be so much smaller than 0.5 that when we subtract it from 0.5, it's essentially going to be the same number, right? So if we can ignore subtracting x from 0.5, do you think we can also ignore adding x to 0.5? Yes, right? So if we do that, so we ignore the guy on bottom, then we can also make that exact same approximation on top. So we can also ignore this guy. Then this simplifies down to 1.2 times 10 to the minus 2 is equal to 0.5 times x all over 0.5, nothing. So now what happens here? The 0.5s cancel these guys out, and we are left with x equal to 1.2 times 10 to the minus 2. Okay? So now, you at some point in time may be tempted to take the minus logarithm of that and say, that's my pH, right? What would be erroneous with that thinking? Right, so equilibrium value of H3O plus was 0.5 plus X, right? We just solved for X, so that is not the equilibrium value of H3O plus. To determine H3O plus at equilibrium, H3O plus at equilibrium, we will now take our 0.5 and substitute our X in, plus 1.2 times 10 to the minus 2, which gives us a 0.5, fighting with myself, a 0.512 molar for H3O plus. And now what I want to do if I want the pH of this solution, I would take the minus logarithm of this number, right? So pH is equal to minus log of 0.512, which gives me a pH equal to 0.029. So fairly acidic solution. Yay. Okay, one thing to note. What was X equal to long term that we just solved for in that second or final ionization for H3O plus? Yeah, X was equal to Ka2, right? So what I meant by that fully deprotonated conjugate base, this guy, equal to Ka2, no matter what type of polyprotic acid you're dealing with, the fully deprotonated conjugate base is always equal to that final ionization constant because of all of these simplifying approximations that we can make. Okay? So again, just keep that in the back of your mind. All right, are we good here? I'll let you take a moment. Okay, let's go ahead and try one on our own. This is not sulfuric acid. This is carbonic acid. I give you a concentration, and I want to know, first off, what is the concentration of carbonate ions in a 0.18 molar solution of carbonic acid. I give you both of the Kas for both of those ionizations, and then I want to know what is the pH of the solution. So this is a two-part problem. So go ahead and try it. It's very similar to sulfuric acid, except a little bit different. Okay, so go ahead and get your answers in. I think there are some misconceptions regarding the pH of the solution. Okay, so I'll go ahead and finish this, and we'll go over this one. Okay, so when I started talking about these, I had said, okay, for the most part, there is only one polyprotic acid that you can assume the first ionization is strong, right? Was that carbonic acid? No. What else would give you a big indication that this first ionization is weak, where you'd have to go through an ice table, an equilibrium problem, to solve for the concentration of H3O+. Ka is small, very small, 10 to the minus 7. So this is super small, okay? So I see a lot of people taking the concentration of H2CO3 and just taking the minus log of that and thinking that is the pH of the solution. But that is incorrect. You can only do that if you're dealing with a strong acid. This is not a strong acid for either ionization. So instead, what you have to go through with this problem is an equilibrium chart, right? An ice chart, over and over and over again, okay? So for the first problem, if I wanted to get at the concentration of CO3 2-, how many separate equilibrium problems would I have to go through to figure out that concentration? 2, right? Because again, this is a diprotic acid, so the first ionization is going to undergo its little reaction, and then I will finally get to this guy in the second ionization, okay? But what did I tell you? You could always assume about the concentration of the fully deprotonated conjugate base. All right, so this guy is always going to be equal to, for this problem, the second Ka, right? So second Ka here was given to us. This was 5.6 times 10 to the minus 11th. That is going to be equal to CO3 2- concentration, okay? I'm going to go ahead and do this, as annoying as it's going to be, go through both ionizations to show you again that that last concentration, CO3 2-, is equal to Ka number 2, okay? Now we're going to start knowing that the first ionization is also very weak, okay? The concentration of our fully protonated carbonic acid initially is 0.18 molar, okay? So we go no water, we don't care about it. And for this first ionization, what should I assume about the concentrations of my products initially? They're both 0, right? So the first ionization, we have not made anything yet, okay? So we're going to assume these guys are 0 initially. We're going to represent our change as x. So we have a minus x, plus x, and a plus x. In an equilibrium, we're left with 0.18 minus x, and x. So now to solve for x, what do? I take my little values at equilibrium in terms of x. I plug them into my Ka expression, right? I have the value for Ka. So 4.3 times 10 to the minus 7th is equal to x times x all over 0.18 minus x. Again, a very smart thing to do here would be to ignore this little tiny x. And so when I do that and I solve, I multiply 0.18 on both sides and I take the square root, I get an x value equal, what is it? 2.78 times 10 to the minus 4th. Okay? So right now, that's my concentration of H3O+. That is also my concentration of my singly deprotonated carbonate or bicarbonate ion, the single deprotonated conjugate base. So now in the second ionization, I'm going to do this. I know everyone's probably sighing because it's so boring, and I've already gotten to the point. So why am I walking through all of these steps? So in the second ionization, we have our conjugate base. It's also going to lose a proton to form H3O+. plus CO3 2-. this has its own little Ka, right? So its own little Ka here is 5.6 times 10 to the minus 11th. So now we'll have to undergo our second equilibrium problem, because this is a diprotic acid. What do I have from the first ionization that I can contribute to my second ionization, my second ice chart? Right, I've got my HCO3. We know its concentration. So this is 2.78 times 10 to the minus 4. We can also ignore this guy. What else do I have? H3O, right? So this is 2.78 times 10 to the minus 4. And we can assume carbonate initially is 0. So we do this whole same thing over again. We have a minus X. We have a plus X. We have a plus X. And in equilibrium, we have 2.78 times 10 to the minus 4 minus X plus X, and then X. So now we'll take these guys. We'll plug them into our equilibrium constant expression for our second ionization. 10 to the minus 11th is equal to times 10 to the minus 4th plus X, slide this guy over, times X, all over 2.78 times 10 to the minus 4th minus X. Again, simplifying approximation. X is very small. So what are we going to do? We're going to ignore it on top as well as on bottom. Okay? So we're going to ignore this guy. We're going to ignore this guy. And if we do that, if I take my little eraser here and I just go in and I take them away, what's going to cancel? The 2.78 times 10 to the minus 4th. They're going to go away, and we're going to be left with X is equal to 5.6 times 10 to the minus 11th. Okay? What's the concentration of carbonate? Ka2. Proves it perfectly, right? Concentration of CO3 2 minus is just Ka2, like I've said already before. But also, I had also said one important thing, right? For everything except sulfuric acid, do you ever have to include the second ionization in determining the pH? No, because it's so small, right? This, to get our overall concentration of H3O plus, to get our pH, if I take this tiny number and I add it to 2.78 times 10 to the minus 4th, what am I going to get? 2.78 times 10 to the minus 4th, bunch of whatever numbers, and then we actually get this contribution to the second ionization. Okay? So if I took the pH up here, my pH would have been equal to 3.56. And if I had added this guy in at the very bottom and I took the pH would have also still been equal to 3.56, because that plays such a small role in this actual concentration that you don't ever even have to consider it. Okay? So 2 lessons that we've learned about polyprotic acids. Number 1, what's the concentration of the fully deprotonated conjugate base? Ka2, or Ka, whatever the last Ka is, right? Second thing we've learned, besides sulfuric acid, do you ever have to include any of the subsequent ionizations past the first one in calculating pH? No. Okay? But unfortunately for sulfuric acid, you do have to consider the second ionization in calculating pH. Okay, all right. So that is that. Is everyone good with that? We're going to come back to similar type problems in the next chapter, where we have these various things canceling, etc. But we'll come back to them in a second. So we'll move on from this. Okay, so a couple more topics we have to talk about. It just continues on and on forever. This last 2 sections, we're going to talk about how we can qualitatively predict the strength of an acid. Okay, so without any type of Ka value or without any type of chart, how we can kind of compare acids and know which one was going to be the strongest. And then the last little bit, we'll talk about the definition of a Lewis acid and a Lewis base, because that is another acid-base definition that you guys should be familiar with. Okay, we're going to first start by looking at qualitatively how we could predict the strengths of acids. So if I wanted to say quantitatively, I want to say, hey, is this a strong acid or not? How would you know that? There are 6 of them, right? So if there's one of the 6 ones that you guys have remembered, then you know it's a strong acid. What if I have two weak acids, and I told you, hey, these both are weak acids? I want to know which one is the strongest. How do you think you'd go about doing that if you didn't have the Ka? So this is what we're going to cover here. This is the entire purpose of this section, is qualitatively being able to predict how strong or weak an acid is just based on its position in the periodic table. So this is going to kind of go back to periodic trends. What were periodic trends? It was being able to predict various physical and chemical properties just based on the position in the periodic table. That's what we're going to be doing with respect to predicting these acid strengths, okay? All right, so let's say that we do have some sort of weak acid. What's going to tell us how weak or strong this weak acid is has to do with this guy's conjugate base. If I want to just predict what the conjugate base of HA looked like, what would I do? Because we struggled with this in our last activity. We Googled it a lot. If I wanted to know what is the conjugate base of this guy, what would I need to do? Pluck off an H, right? And H is also going to take away a plus with it. So what am I left with? Just A minus, right? So the conjugate base of our weak acid here, this is our conjugate base, is just an H removed, putting on a minus sign, okay? Okay, so in predicting the strengths of these acids, it's all going to hinge upon the conjugate base of what we're looking at, okay? So this guy is our conjugate base. We have a negative charge associated with this conjugate base, which is bad. We tend to not like to put charges on things, okay? So this guy's going to tell us how strong or weak our weak acid is based on its stability. So the more stable this guy is, the stronger the acid is, okay? The easier the conjugate base could be with that negative charge on it, the easier the acid is going to pop off that H and actually produce it, okay? So what is going to determine how stable a conjugate base is? So we're going to look at a couple different things. The first one that we're going to start with is the conjugate bases of binary acids. So what was binary acids again? Binary meant an H bound to what? Multiple things, polyprotic acids or polyatomic ions. Was that what a binary acid had to do with? No, it's just an H bound to one other type of element, okay? So when we're looking at these first, to start with, we're going to be looking at acids that have a hydrogen bound to one other type of element. So what are the things that are going to predict how stable this is? The first thing we're going to look at is electronegativity of that other element, okay? The more electronegative it is, the more it likes to have electrons around it, the more capable it's going to be of stabilizing that negative charge. What are our trends in electronegativities? Going back to periodic trends. So electronegativities, as we move from left to right, what happens to electronegativity? Who is the most electronegative element in the periodic table? Loves electrons. Can't get enough of them. Fluorine, right? So fluorine is the most electronegative element in the periodic table. Who is the least electronegative element in the periodic table? Right, this guy down here, francium, okay? So what is our trends? As we go from left to right, we're generally going to increase in electronegativity, right? So things over here love to have electrons. What happens as we go from top to bottom? We decrease in electronegativity, okay? So, again, things that are electronegative love to have electrons around them, so we're going to be very capable at stabilizing that negative charge, right? So things that are very electronegative are going to make great conjugate bases, meaning that their acids are going to be stronger, okay? So if I said, who's going to be a stronger acid? Ammonia, NH3, or HF, who would you tell me, based on the stability of the conjugate base? Who's going to be more stable, F minus or NH2 minus? Who's more electronegative, F or N? F, right? So F is more electronegative. It's going to be more stable. It's going to produce the stronger acid, okay? The more stable the conjugate base, the stronger the acid that it generates from. So number one is electronegativity. Number two, what is the other little element that we have to consider when looking at the strengths of binary acids? Polarizability is the second thing. And this is a fancy little word. But really, polarizability, what it really means is how big is the atom, okay? So if we look at our halogens, so our 7A, so we have F, Cl, Br, I. Is HF a strong acid? No. But what about the other ones below it? Those are all very strong, right? HBr, HCl, HI, okay? Can we explain that in terms of electronegativity? No, right? Because as we move from top to bottom in the periodic table in terms of electronegativity, we actually see a decrease. Fluorine, again, is the most electronegative element. So what's explaining the fact that fluorine, or HF, is actually not a strong acid, but everything below it is? So now compare the sizes of these guys where this negative charge is going to lie, right? Fluorine's a very, very, very small atom. If it has a negative charge, even though it loves to have electrons around it, it doesn't have a lot of places to put that negative charge, right? But as we go down, what's going to happen to the atom strength, or atom size, pardon me? They're going to get bigger, right? You're going to get bigger, more orbitals, more places to put these electrons, right? So when we go down to HCl, Cl minus isn't as electronegative, but it's bigger. Has a lot more places to put that negative charge that's going to form. So because of that, it's more stable, and HCl is a stronger acid. As we go all the way down to HI, in this list, HI is the strongest acid because I is gigantic, right? It's got lots of orbitals, lots of electrons. If we add one little tiny electron to it, it's not going to do anything. It's got lots of places to put it. Because of that, HI is a strong acid because I minus is very stable. It's large, it's electronegative, it loves to take electrons, and it has lots of places to put them. Okay? So number one, when we're looking at acid strength, we're looking at stability of the conjugate base, electronegativity. Okay? Number two, we're looking at polarizability, or just overall size of the atom that we're trying to put this negative electron on. Okay? So again, if we were looking at comparing acid strengths, and I asked you, who was the stronger acid, water versus H2SE, who would be the stronger acid? Who has the more stable conjugate base? H2SE, because again, it's larger and it has lots more places to put the negative charge. This is the more stable conjugate base, so that means it is the stronger acid between the two. Okay? Okay, so that's for binary acids. I'm going to finish this off. What are the other types of acids? So we have the HBr, HCl. What is the other type of acids? The oxyacids, right? So oxyacids were the acids of the polyatomic ions. Where is the proton that these types of acids, where is it at? Is it at like on a C, or is it at on an F, or who is it really on? The proton that these oxyacids are losing. All of these guys, the proton that is popping off is always on an oxygen, okay? So for things like H2SO4 and H2CO3, all of these oxyacids, the proton that's popping off is always on an oxygen, okay? So if we're looking at the atom that oxygen is bound to, or the atom that hydrogen is bound to, being the thing that's going to determine the acid strength, they're all going to have the same atom, right? So we can't look at, oh, who's more stable? O minus or O minus, right? Because they're all going to be the same. So now we have to look at a couple of other different elements that are going to affect the stability of these conjugate bases. And the next thing that we're going to look at is who is the O attached to, okay? And the idea behind this is what we're going to call induction. This inductive effects, induction versus inductive effect, okay? So again, the conjugate base of whatever this guy looks like is going to be a Y to an O that's going to have a minus charge on it, okay? This is our acid, and we're looking at the strength of this conjugate base, the stability of this conjugate base. Now, if I have something in this Y position like a carbon bound to an oxygen, how electronegative is carbon comparatively on the periodic table? If we're looking at just electronegativity, so does carbon like to pull the electrons towards itself, or does oxygen actually like to pull the electron towards itself in this bond? Oxygen, right? Oxygen's so much more electronegative, right? So carbon is not going to be very good at stabilizing this negative charge that's on oxygen. What if, on the other hand, this Y wasn't a carbon, but was something like fluorine, right? So fluorine is more electronegative than oxygen, right? So if we look at this bond, fluorine is pulling more of the electrons towards it. So we're going to start seeing a partial negative charge developing on the fluorine, a partial positive charge developing on the oxygen. And so essentially, this negative charge that's on the oxygen is going to be able to spread out between the two, right? Fluorine is pulling that extra electron density towards itself, so that's spreading out that negative charge over multiple atoms. Which one do you think is going to be more stable? The negative charge that lies solely on the oxygen, or the negative charge that's kind of distributed between the fluorine and the oxygen? Distributed, right? So if we have some sort of nice electronegative element attached to our oxygen that's going to help essentially pull that electron density towards it, that's going to be more stable than something that can't do that, okay? So what we're looking at here is the atom that is bound to the oxygen. The more electronegative this atom is, the more stable the conjugate base, the stronger the acid. So more electronegative, more E negative, more stable the conjugate base, the stronger the acid. And you can see that when we compare and going down the various charts, Cl versus Br versus I, right? This guy, this hypochlorous acid, is the strongest acid because, again, chlorine is the most electronegative, right? Comparatively to hypobromous acid, bromine is not as electronegative as chlorine. So because of that, this guy is our stronger acid. One other thing, and then I'll be done, I promise. So oxyacids, the atom that is bound to the oxygen where the proton is coming from, the more electronegative that thing is, the stronger the acid is going to be. There's one other little central player with respect to this. Again, looking at the atom that the oxygen is bound to, where the proton is coming from, the more oxygens that are on that atom, the stronger the acid is going to be. Okay, so for example, we could go through our little CLO chart, so hypochlorous versus chlorous versus chloric versus perchloric. How are these guys differing with respect to the atom that is bound to the oxygen that's losing the proton? So this guy has, this chlorine has 0 oxygens besides the first. How many oxygens does this chlorine have besides the one who's losing the proton? 1. As we continue to increase, what are we doing to the number of oxygens that are on that central atom? We're increasing them, okay? So as we do that, what happens to the acid strength? It gets stronger, right? So the more oxygens that we put on that central atom, the stronger the acid we're going to have. And again, this has an inductive effect, right? This has an electronegativity effect. As these oxygens are pulling electrons towards it, it's going to help stabilize this negative charge that develops. But also, this has to do with resonance structures. Does anyone remember what resonance structures are? Somewhat. Okay, so when you get into organic chemistry, hopefully they will explain acidity and basicity based on resonance structures, but I'm not going to today. All I'm going to tell you is the more oxygens that are on this guy, the stronger the acid is going to be, because again, it's going to make a more stable conjugate base. Okay? Okay. So I think I'm going to stop there. You guys have a couple more minutes. Acid-base theory. Okay, so Lewis acid-base theory. So we've talked about Arrhenius, right? Arrhenius acid-base theory is what we introduced you to in 151, and that we have talked ad nauseum about Bronsted acid-base theory. Bronsted-Lowry acid-base theory, okay? So in Bronsted-Lowry acid-base theory, what are we focusing on? Proton, right? But comparatively to Arrhenius, what's the difference? We're looking at what happens in the chemical reaction, right? And so what are we focusing on with respect to protons in a Bronsted-Lowry acid-base reaction? The transfer of protons, right? So we define a Bronsted-Lowry acid as a proton donor, a Bronsted-Lowry base as a proton acceptor. And that's what we're focusing on in Bronsted-Lowry acid-base theory, okay? So now we're going to move into this very last theory of acids and bases, and this is Lewis theory. And it's going to be very similar to Bronsted-Lowry acid-base theory, except now, instead of the proton, we are going to be focusing on what happens to the lone pair of electrons, okay? All right, so in in Lewis acid-base theory, a Lewis base is an electron donor, okay? So a Lewis base is an electron donor, and a Lewis acid is an electron acceptor, okay? So in this little above reaction that we have right here, we have our proton reacting with NH3, okay? So Bronsted-Lowry, proton is the acid, right? We transfer the proton to our base, NH3. But in Lewis acid-base theory, who is the base? Who is the proton donor? Who is the electron donor? Who's donating their electrons in this overall reaction? NH3, right? So it's, again, this guy, our NH3, is still the base, right? It doesn't change with respect to Bronsted-Lowry versus Lewis. NH3 is still a base, except now it's doing something different. It's not accepting a proton, it's donating a lone pair of electrons. Still a base, regardless, okay? On the other hand, proton, H plus here, what is he doing in this chemical reaction? Instead of being transferred, what is he accepting? Electrons. He's accepting a lone pair of electrons. So this is our electron acceptor. So again, this is still our acid. Acid, base, those names don't change. Just the definition of what makes them an acid and a base changes, okay? So in Lewis theory, electron donors are bases, and electron acceptors are acids, okay? All right, so what are kind of the characteristic traits of Lewis acids and bases? So we're going to start with bases. And so in general, Lewis bases are the exact same characteristic traits that we see with Bronsted-Lowry acid-base theory, right? What is the big idea behind a Lewis base? We have to transfer a what? A lone pair of electrons, right? And in Bronsted-Lowry, what did we also still have to accept a proton? A lone pair of electrons, okay? So Lewis bases are pretty much the exact same thing to Bronsted-Lowry bases. They have to have an excess of electron or a lone pair of electron with which they can donate. Under Lewis base theory, it was the exact same thing with Arrhenius because they had to have a lone pair of electrons which they could accept a proton with, okay? So Lewis bases, Bronsted-Lowry bases, pretty much the exact same thing. Just as a note, for Lewis acid-base theory, things that are negatively charged tend to be better Lewis bases than things that aren't, okay? So that means an excess of electrons. And things that are bigger tend to be better bases, right? So we talked about this last time with respect to predicting whether or not an acid was strong. So things that are very polarizable tend to be very good Lewis bases. So sulfur, because it's more polarizable, it's larger, is going to be a better Lewis base than something like oxygen, which lies just above it in the periodic table. Okay, so those are bases. Now, Lewis acids are going to be slightly different, okay? So what was the big characteristic trait under Bronsted-Lowry acid-base theory? An acid had to have what? It had to have, we're donating something in BL, in Bronsted-Lowry acid-base theory. What were we donating? Protons, right? So what did an acid have to have? Hydrogen. It had to have a proton with which it could donate. But the thing about Lewis acids is we don't have to care about protons anymore, right? So this is essentially going to define acid-base chemistry without the presence of protons, okay? All right, so what do Lewis acids actually have to have? Number one, they need to be electron deficient, okay? So they either need to be attached to a very electronegative atom or they need to just kind of be electron deficient in their overall state. They have to have an empty orbital with which they can accept these electrons into, and we'll talk about that in a second. And then they tend to like to be positively charged, okay? So Lewis bases like to be negatively charged. Lewis acids tend to be better if they're positively charged and electron deficient. Okay, so now let's understand, ideally, a little bit of this Lewis acid-base chemistry. okay? So I have two different reactions here. I'm going to explain how this is a nice Lewis acid-base reaction. So in this first reaction, I have my NH3 molecule, okay? And this is reacting with BF3, okay? So NH3 has our nice lone pair of electrons with which it is going to donate, okay? So this is going to be our Lewis base. It's a Lewis base because it's donating a pair of electrons to this boron. Boron, in this molecule BF3, is our Lewis acid, right? So again, if it's a Lewis acid, it needs to be kind of electron deficient. Why would boron be electron deficient? So does anyone remember back to molecular geometry? Drawing the Lewis structure of boron, right? So what was the thing with respect to boron, with respect to Lewis structures? Boron was okay not having an octet of electrons, right? So boron was fine just having 6 electrons around it in the Lewis structure, right? What does that mean that boron has open and willing to accept electrons with? An empty p orbital, okay? So in this structure, boron has this beautiful little p orbital with which it is willing to accept electrons from our NH3 molecule, okay? So boron is electron deficient, it doesn't have enough electrons around it, and so because of that, it ends up being a great Lewis acid. Okay, so one more example. We have water. Water down here is acting as our Lewis base. It is transferring electrons to this carbon, right? Carbon in CO2 is our Lewis acid. Why would carbon be electron deficient in CO2? Who is carbon attached to in these bonds? Oxygen, right? And so comparatively, between carbon and oxygen, who's more electronegative? Oxygen. Oxygen loves electrons, especially compared to carbon. So we've got a bunch of electrons going this way, a bunch of electrons going this way, and it leaves this poor little carbon with not a lot of oxygen or not a lot of electrons around it. Okay, so because of this, carbon in CO2 is electron deficient, so it serves as a very good Lewis acid. Okay? Notice that all of these guys are also Bronsted-Lowry acids and Bronsted-Lowry bases if we had a proton to actually donate with, right? So this would also be a Bronsted-Lowry base, but CO2, would it be a Bronsted-Lowry acid? Would this guy be a Bronsted-Lowry acid? No, it doesn't have a hydrogen. Okay, so again, the whole idea behind this is Lewis theory helps us understand acid-base chemistry when we're not dealing with things that have protons. All right? Okay, with respect to this, you'll see plenty of it when you take organic chemistry next semester. So we'll leave it at that.